Light scanning is one of the critical components of multiple projectors and imaging systems. Examples include laser projectors, fluorescence microscopy, and LiDAR. We show how to make light scanning 1,000 times faster using a low-cost system without moving parts to improve the scan speed of all these applications. Our new Megahertz light scanning technology works by putting together the physics of sound, light, and matter interaction, ultra-fast optics, fast synchronization electronics, and signal processing algorithms. Here is how all of this works. For simplicity, we will start with some 2D visualizations. Our prototype consists of a compressible medium such as water. If we send light rays through this medium, they will of course just travel straight. We will show how to focus these light rays and change the focus at the megahertz rate. For that, we place a transducer in this medium. By driving the transducer with a sinusoidal voltage, we vibrate the transducer at a scale of tens of nanometers. This produces ultrasonic pressure waves inside the medium. In turn, these pressure waves change the refractive index of the medium, which is now proportional to the local pressure. Because of the spatially varying refractive index, if we now send light rays through this medium, they'll continuously curve and focus. As the sound waves travel away from the transducer, the refractive index also moves at the speed of sound in water, moving the focused light at the same speed. While the focus is steered at high speed, we do not yet have any control over where the focus happens. To control the focus, instead of a continuous wave, we use a megahertz pulsed light source. We synchronize this source with the ultrasound phase. This allows us to control which focus locations we scan. For example, here we are illuminating a fixed position. In the second example, we are illuminating two positions. So far, we have been visualizing everything in 2D. In practice, in 3D, we have a planar transducer that focuses light on a line and not on a point. What we do is we use two orthogonal planar transducers that produce a focus at the intersection of two lines, which is a dot. We also restrict illumination to one focus region to get a single point focus. As before, we control the location of this focus point by pulsing the laser and synchronizing it with the changing ultrasonic phase of now two rather than just one transducers. This gives us more degrees of freedom, which makes it possible to realize different scanning algorithms. We show a few in detail in the paper. Let's see some real results. For this, we built a hardware prototype that operates in megahertz range, which we used for proof of concept experiments and comparisons with standard galvo mirrors. In the first experiment, we project a series of 100 dots that form the letter A, both with standard galvo mirrors and our ultrasonic scanner. We do this projection during a single camera exposure. In 1 millisecond exposure, the galvo mirror only manages to project a single dot, whereas our ultrasonic projector projects the entire letter A 10 times, demonstrating that our prototype is 1,000 times faster. Even at a 50 millisecond exposure, the galvo only projects an incomplete shape. In the second experiment, we use our scanner in a LiDAR prototype, such as those commonly found in autonomous cars. Using our prototype, we raster scan a scene of 100 by 100 points at 5,000 frames per second. This is 50 million points per second. Compared to this, a standard commercial scanning LiDAR could only scan 500,000 points per second. Our system is 100 times faster and can faithfully reconstruct both photon counts and depth values. In addition to raster scanning the entire scene, our scanner makes it possible to quickly scan arbitrary points in the scene. To demonstrate this, we create a 3-point scene and image it to compute the per point lateral locations. We then scan the depth of the 3 points using both the galvo and our technique for a total time of 3 milliseconds or 1 millisecond per point. When standard galvo scans these points, it spends most of its time traveling from one point to another. As a result, most pulses fired by the laser are wasted during the travel time of the galvo. On the other hand, Our technique is very fast and does not waste even a single photon. As a result, our technique has 15 times higher depth accuracy than Galvo's. As this is still a first of its kind experimental prototype, it has some disadvantages. For example, as I mentioned earlier, the use of two transducers creates a cross-shaped point spread function which shows up in all our results. The use of liquid water as a modulation medium may be undesirable for some applications. As we discuss in the paper, these are engineering challenges that can be overcome with further development. We hope that our results will motivate such an effort. To summarize, we built a megahertz light steering technique with no moving parts. Our technique improves the scanning speed of the dot projector by 3 orders of magnitude, LiDAR scan speed by 2 orders of magnitude, and depth accuracy by 15 times. Thank you for listening.